Hi everyone, so this is our second video on econometric analysis, and if at any point in this video you want to go back to the first introductory video to econometric analysis, then you can click this video 1 button up here in the top right corner and it will bring you there. And I recommend you watching that video first if you have not seen it. So this is sort of a formal introduction to the simple linear regression. We're going to touch on the differences between the population and sample regressions, discuss interpretation of the model and what it takes to be able to assume causality. And then we're finally going to discuss residuals and the derivation of our coefficients. So in the last video, we sort of introduced this as our simple linear regression model. Y is equal to beta 0 plus beta 1 x plus u, and we can call this our population regression function, and this is sometimes denoted as PRF. And what it is it's our true model. It's what y is actually represented as in a functional form. So this is what we're trying to find, and we will never truly know what our population regression function is, but we try our best to find it using our sample regression or our estimated regression. So we try our best to estimate this. And just some terminology first. Y is also sometimes referred to as the dependent or the explained or response variable. X is also sometimes referred to as explanatory or the regressor, and U, our error term, is also sometimes called the disturbance or unobservables. And so your textbook or professor might use some of those terminology instead, and might be beneficial for you to know all of them. The sample, visually the only difference is that there's hats on top of all of these intercepts and variables and coefficients. And in this version, the U hat is no longer called our error term. It's usually referred to as our residuals, and it's sometimes denoted as an R or an E, also depending on your textbook or professor. And so this brings us to our interpretation of these coefficients. And we sort of touched on this in the last video, but we're going to go a little bit more in depth. I'm not going to write anything for beta 0, but we will discuss more in words, I guess. So if x is equal to 0, then we know that our dependent will be equal to beta 0. So if we have an example, I guess, say wage is equal to beta 0 plus beta 1, education plus our error, whatever. If education is equal to 0, we want to know what our wage will be, and our wage will be equal to our beta 0. For our beta 1, it's slightly harder to interpret, but it's nothing we can't handle easily. So if we take the derivative of y in respect to x, we will obtain beta 1. So this is what we will obtain if we have a causal relationship. So if we take the derivative of this, we can break this down. If we take the derivative of this, this is just a constant, so it will become 0. X has no exponentials, and so this whole term here will just become the coefficient, which is beta 1. And then if we have a causal relationship, we have to assume something called the conditional mean independence assumption, which essentially means that the derivative of u in respect to x is equal to 0. And it's sometimes also shown as the expected value of u given x is equal to 0. So this just means that u is not dependent on x. So there's nothing in this error term that affects x. So if we were going to go back to our example, we had wage is equal to some constant plus beta 1 education plus u. And we cannot assume that this is a causal relationship. And that does not mean that education does not affect wage, because it definitely does. Of course it does. But what it means is that causal means that there's nothing in u that is that education is dependent on. But we can sort of use our intuition to say that you will probably have things such as ability, and ability is generally correlated very strongly with education. And because this is in this error term, we didn't include it in our regression, then we will not be able to assume the conditional mean assumption, and therefore these coefficients here, beta 0 and beta 1, will not be completely correct. They might be overestimated or underestimated depending on the omitted variables. So omitted variables we'll get into much later. But that's just sort of an introduction to why we cannot assume causality all of the time, which is important to know. So this brings us to our visual representation, and we sort of did this last time, but we're going to do it a little bit more formally. So we have our independent variable x and our dependent variable y, and we have all this data. Put some bigger ones out here, and then we run our regression and we get this line that looks something like this, where this would be our beta 0, the slope would be our beta 1 hats. And now we can take some x here, we'll call it xi, and at this point, say there's a point here, at this point we can go up to here, and this distance is our yi, so it's what we actually observe. It's our data. Our data says that this point is at yi and xi. But what we estimated was all the way up here. And so this distance from here to here is actually our yi hat. So it's what we estimated. And then the difference between the two is our ui hat. So this is a more formal, I guess, visual representation of what we're actually doing. So these are our estimations, because we can't actually know the population. But what we can do now is give a formula for what the residuals are, now that we have this. So we know that ui hat is this, which is the difference between these two things. And so we have this is equal to yi minus yi hat. And then if we plug in our regression for yi hat, what we obtain is yi minus beta 0 hat minus beta 1 hat x I. And so this here is what our estimated residual is at this point. And now that we have this formula, what we've been leading up to this entire time is sort of a informal derivation of our ordinary least squares estimates. And so what I'm saying is, how can we estimate this beta 0 and estimate this beta 1? How can we get a good estimate for both of them? So what we do is we minimize the sum of all of these squared. And this here, just on a note, the ui squared summed up is called our sum of squares residuals, which is often denoted as an RSS or an SSR. It really depends on your professor book as well. So make sure you just get your terminology correct. And so when we minimize this sum of squared residuals, we're essentially trying to get the best line here in our regression. And when we do that, we're not going to go into the full derivation of the coefficients, but in OLS we obtain a beta 1 hat equal to the covariance of x and y all over the variance of x. So in OLS, you will generally be able to find this. Given any data set, you'll be able to find the x and the variance of x and the covariance of xy, and that is what will give you your beta 1 in a simple linear regression. And it's as simple as that. And then the beta 0 hat, once we get that, we will be able to obtain the beta 0 hat, which is equal to the mean value of y minus the beta 1 hat. So what we obtained here, we can plug it in right here, and then multiplied by the mean of x. So that's how we find our coefficients in our estimated regression. And I hope you understand a little bit more on what they are and what they mean. And I hope this visual representation helped a little bit to understand what the residuals are and what they mean. And I hope you sort of understand the interpretation of the model and what it takes to be able to assume causality. So if you remember, causality was, we had to assume that there was nothing in this residual that was correlated with the x. And then I also hope you understand the difference between population and sample regression. So sample is what we can estimate these hats, and then the population is what we never observe. It's the true model that we're trying to find, the functional form that we truly want to find. And yeah, I hope you understand a little bit more about the simple linear regression, and our next video will be up soon. Please subscribe and like and comment with any questions.